So once again, my name is Christian Sasse. I'm the astronomer in charge for iTelescope, and I'm very pleased today to introduce you to a quite exciting topic all about SETI. Is there anybody out there? So without further ado, I'm going to introduce to you Macy Huston, who is a Ph.D. candidate from the Astrophysics and Astronomy Department of Pennsylvania University. So Macy, come and join us, please.
Hello.
Hi, Macy. Very nice to have you here. So how is it over there? Is it very cold at the moment? Or?
It's very gloomy outside today.
It is. Well, today we're going to look into space. So this is really exciting. It's a topic that I know many of our viewers are very interested in. Is there life out there? It's what's going on. And it's amazing. You're doing your PhD topic on this. Is that right?
Yep.
That's astounding. So you're one of the world experts now. So that's incredible. So anyway, without further ado, Macy, the floor is all yours. And yeah, you can share the screen, and I'll be quiet now. Go ahead, please.
All right. Are my slides up?
Yes, it's all good. Go ahead. Yes.
Okay, great. Yeah. So today I'm going to talk about SETI and really try to explain, and hopefully everyone will understand how astronomers search for technological life in the universe. So I kind of wanted to start with thinking about this from the opposite direction. So I want to think about, if there's alien life out there in the universe, how might they be able to detect us on Earth today? Because we have all kinds of technology going on. So this is something that we would call a technosignature, which is just a fancy word for a sign of technology. And maybe our most powerful, most detectable technological signal on Earth would be radio transmissions or radio leakage. So maybe the most obvious example of this has been the few intentional messages that humans have sent out to space in what we call METI, or messaging extraterrestrial intelligence. So there was this Arecibo message that was sent a while back. But METI isn't really something we do very often. We're not usually trying to reach out to extraterrestrial life. It's a very controversial idea, actually. A lot of people don't want to do it at all. Some people really do, but just in general, we have sent a few intentional messages, but we don't very often. But we are very regularly sending radio transmissions around Earth and into space just for our own human purposes. So, for example, we're constantly using radar to track things like asteroids and various spacecraft and weather. We're sending radio transmissions to and from different parts of the solar system to study planets all the time. And so, these radio signals are going out to space, and they're something that could maybe be detectable by other alien life, even if they're not our intended target. And in addition to messages we are sending out into space, we also have this constant radio emission going in all directions from things like our cell phone towers and TV towers. So our radio emissions from Earth are very powerful as a signal of our technology in the universe. Another way that you might detect humanity is from our atmospheric pollution. So there are certain gases in our atmosphere here on Earth that are produced by our industry and by processes like combustion. And so there are things in our atmosphere like carbon dioxide and nitrogen dioxide that we produce through our industry, through our technology. And then there are also molecules like chlorofluorocarbons, which some of those have been banned, but not all of them, because they were harming our ozone layer. But there are certain molecules like chlorofluorocarbons that we don't know of any natural way to produce them, only technological. So those existing in our atmosphere is a pretty distinct sign that we have technological life here on Earth. Another technosignature that we produce on Earth is our city lights. So if someone were to look at the dark side of our planet, the part that's pointed away from the sun, it shouldn't be very bright because it's not going to be reflecting any sunlight. But we are producing all of these artificial lights, and you might even be able to see certain spectral features based on the types of chemicals that we use in our lighting systems. In addition, here on Earth, we are surrounded by a ton of artificial satellites that we've created, and this number is increasing very rapidly in a way that is becoming detectable. And kind of the last thing I want to mention on Earth here today is our lasers. So we don't really point lasers out to space in search of aliens the way we have done radio transmissions a couple of times. But we as humans are regularly pointing lasers out to space. Specifically, astronomers use lasers for adaptive optics systems. So it's basically just a way to study Earth's atmosphere, kind of figure out what's going on with the air at any given time to make our astronomy observations just better and kind of take out the effects of the atmosphere. But we're using lasers to study this, and we're just pointing those lasers directly at the sky, and they're going out into space. If anyone with an optical telescope happened to be at the other end of those laser beams, they could detect that we're here. So before we get further into the other side of this and how we look for life, I want to go through a couple definitions. So kind of the big abbreviation we usually use for this field is SETI, the search for extraterrestrial intelligence. But there's also another important and maybe more specific term I want to define here as well, which we call a technosignature. And this is just any type of detectable evidence of technology. So for example, all of those ones I just listed that we have here on Earth. And so it's really important to note that intelligence and technology are not the same thing. So we'll generally think like it requires some level of intelligence to want to and decide to and know how to build technology. But we also know that intelligence can exist without any technology. For example, there are species on Earth like dolphins and octopuses that have clearly demonstrated intelligence, but they don't use any sort of radio or laser signals. So I want to be clear that in SETI, we don't actually think that those two things are equal. The SETI term just kind of has lingered from when the field first began, but we are very much just focused on finding signs of technology because that's something we can quantify and detect. There's no objective good way to measure intelligence or to detect it from a distance. So I wanted to move on to our poll next and think about the question for SETI, why haven't we found anything yet? So I'll give a minute for the poll.
Okay, there we go. So that's actually disappointing. I thought you were going to say we found something, but we didn't tell you yet.
Oh, we would tell you. We will be so excited. We will tell you.
So we know now there's really no. So you haven't found anything. That's okay. That's clear.
Scientists aren't good at keeping secrets.
Well, you know these conspiracy people that love saying, well, NASA's hiding all this in whatever district.
I don't work for NASA.
I know for NASA. I know.
Yeah.
Okay. Oh, that's a good answer. Okay, we'll just wait a sec and then we'll share the results. Okay, please, everyone, give your opinion. Just wait a few more seconds and then we'll share it. Okay, there you go.
Okay, we did have the winning answer, was kind of the one I suspected. So this question of why we haven't found anything yet is something that people call the Fermi paradox sometimes, although a lot of us like to argue that this wasn't really a big concern that Fermi had, and it's not actually really a paradox either. So if you think about the questions like whether all life, any type of life is rare in the universe, that's certainly possible. It's possible that technological life in the universe is rare. And it's possible that there is all kinds of technological life in the universe that is intentionally hiding from us. But honestly, the best answer is that there's no paradox because we have barely looked. One of the kind of important things in SETI that Jill Tarter of the SETI Institute likes to talk a lot about is this idea of the cosmic haystack, with kind of the analogy that like looking for technology and life in the vastness of space is like looking for a needle in a haystack. it takes a ton of work, a ton of effort, and there's so much to search. So an analogy that Jill Tarter likes to use is that, let's say all of space is all of the oceans on our Earth. The amount of area that we have searched as SETI researchers so far is equivalent to 1 cup of water out of the oceans. And so kind of the way we like to think about this is, if you dip a cup of water in the ocean, you pull it out and you don't have a fish in it, you're not going to conclude from that fish don't exist. But you also can't conclude that they do, right? So there's just so much work left to do in SETI. There's so much of space to search, so many different types of technosignatures, that there really just is a ton of work left to do. And so we've already listed off some of our technosignatures that we produce here on Earth, but it's also really important in SETI that we acknowledge that not all life in the universe, if and where it exists, should be just like us. We should try to think of as many possible ways as we can to look for different signs of life and different types of technology. So for the next part of this, I just kind of want to go through kind of the main 6 categories of SETI search strategies. So the first one, probably the most well-known and the oldest SETI search method, is radio SETI. So this is searching for radio signals coming from space, artificial radio signals from space. There are also natural sources. So SETI, and specifically radio SETI, really launched in earnest around 1960, when astronomers figured out that Earth's current radio telescopes at the time were strong enough to detect signals that our radio transmitters could send from very large distances across space. So this was kind of the realization that if there is other life out there in space, we could communicate with each other using radio waves. So at this time, Frank Drake, who was one of the major early leaders of the SETI field, launched a project called Project Ozma, which was the first SETI search ever performed. He used this 85-foot radio telescope down in Green Bank, West Virginia for the project. And I was lucky enough to go visit it and get the SETI tour just about a month ago. It was really great. And so what he did was point this radio telescope at a couple of the nearest stars to our own and just look for any sort of artificial radio signals. And unfortunately, he didn't find anything, because again, he just pointed at 2 stars for a small amount of time. But ever since then, and into present day, there's a lot of ongoing work in the field of radio SETI. I'm not going to be able to cover all of the different projects doing this today, but I'm going to talk about a couple of the really big ones. So one of these major projects is Breakthrough Listen. It is the largest SETI project so far, and they mostly focus on radio SETI methods, but they also do some other things, and I'll talk a little more about that when we get to those categories. But the biggest thing that they're doing is doing a massive survey looking for artificial radio signals from 1 million stars in our own galaxy, and also from about 100 of the most nearby galaxies. And they're using the most powerful modern radio telescopes that we have, including the Green Bank 100 meter, which you may have noticed as my background on the rest of my slides too. And then kind of the other main radio SETI project I wanted to highlight today is being done by the SETI Institute on the Allen Telescope Array. So the Allen Telescope Array was designed specifically to do SETI, which is a unique thing about that instrument. And so what they actually do with this array is that they add together a bunch of smaller radio telescopes to sum up to basically the equivalent of using one larger radio telescope. And so they are currently underway doing their radio SETI searches. And they're also doing some other science with the Allen Telescope Array too, because it just so happens that most of the science that we try to do as SETI researchers, those observations that we take of the sky can be useful for other reasons too. So some other things that the SETI Institute does with all their data is study things like pulsars, which are fast rotating neutron stars that send radio waves our way periodically, and just other natural radio sources in the sky as well. So this is kind of a running theme in SETI, that a lot of us work simultaneously on SETI projects looking for technology and other projects looking for natural things in space at the same time. So following radio SETI, optical SETI was also one of the early techniques. So this idea is searching for artificial lasers from space. This idea is pretty interesting because it is a lot like the radio SETI idea, where you can use just this electromagnetic waves for communication. They travel at the speed of light, and it was demonstrated at this time, just a couple of years after that first radio SETI paper came out, that Earth's optical telescopes are also capable of detecting the laser beams that we could produce here on Earth at interstellar distances as well. And it's kind of interesting to think about the timeline of how our technology developed here on Earth, and that we developed radio technology a little before laser technology. So radio became very dominant for a lot of our communications here on Earth. But that's kind of just a coincidence, and things may have evolved in a different order on a different planet. And it's possible that there are other species that prefer laser to radio, because that's just what they started doing first. And so laser SETI or optical SETI has not been as widely performed or as popular as radio SETI, but there are a couple of ongoing projects working on it right now. So one of these is going on at the Veritas project. So the Veritas project is interesting because it was not initially designed to do SETI. What the Veritas project does is study gamma rays. So these are higher energy light waves that come in from space, and they hit the top of our atmosphere, and they send down little showers of blue light as a result. So they've built, this is called Cherenkov radiation. And so people have built these telescopes to detect that optical light as a tracer of gamma rays that come from natural sources. But interestingly, the design that you use to make those telescopes just happens to be great for detecting artificial laser pulses. So the Veritas project, while they're doing their gamma ray studies, has also partnered with Breakthrough Listen to do an optical SETI study to look for laser pulses from space. And another ongoing SETI project related to this is PanoSETI. So it's an all-sky laser SETI search. It's still kind of in progress, and they're still putting parts of it together, but they have started doing observations with some prototypes. And they're also just going to be watching the sky for brief laser pulses. And so one of their prototypes actually has detected a laser signal from space. As you can see in the animation here, it is human-created lasers. It's a satellite that we have in orbit called Calypso, but it's a really great demonstration of how, you know, these optical telescopes can detect lasers from space and track how they move in space. So if there ever are sources that aren't human-made, we can see them just like this. The third category of SETI strategies I want to talk about is exoplanetary SETI. So this has been sort of a more recent development. And the idea is to search for signs of life and technology on planets themselves and in planets' atmospheres. So astronomers didn't actually detect the first exoplanets until the 1990s. So this wasn't something people were thinking about in 1960 when SETI began. But it's something people are thinking about really hard now, because we are finding more and more exoplanets almost every day, and it's a very popular field. And we're finally kind of developing technologies where we can study those exoplanets in more detail. So something we think about in SETI is how might any technology that exists on these planets affect how those planets appear to us? So one of the ways technology can affect a planet is that it can produce certain gases in a planet's atmosphere. So there's a technique we use to study planets' atmospheres called transmission spectroscopy. And basically, this is just when a planet passes in front of its star, some of that starlight has to pass through the planet's atmosphere. And based on what kinds of light get absorbed by the atmosphere, we can learn a little bit about what the contents of that atmosphere are. So we can see in this example here of a transmission spectrum of an Earth-like atmosphere that this is a great way to identify planets that have things like water and carbon dioxide and ozone and methane. And so this is a way that we can search for signs of technology and industry in atmospheres. And it's also a way to search for signs of biological life, because there are things like oxygen and other molecules that are we think are very related to life. So one of the really great things about this method is that you can search simultaneously for biological life and for technology. And it's really important in the search for extraterrestrial life that we're looking from a lot of different angles for a lot of different types of life. So looking simultaneously for technology and biology is a really great way to search for life in the universe. As I mentioned before, another thing that might be detectable on a planet is night-side city lights. So just kind of artificial brightness on a part of the planet that should be dark. Now, the thing about exoplanetary SETI is that it's pretty new, and the technology we need to do this well is kind of still developing. So you've probably heard a lot recently about the James Webb Space Telescope that just launched in the past year. It is performing transmission spectroscopy to characterize the atmospheres of exoplanets right now. But just due to technological limitations about where we're at right now, it's really only able to study in detail kind of larger, hotter, close into their star exoplanets than those that we think are likely to harbor life. So we don't necessarily think that JWST is what's going to get us to the point where we detect technosignatures and biosignatures in exoplanet atmospheres, but it's a really important technological development along the way there. So kind of the next generation after that of transmission spectroscopy telescopes, like there's this proposed concept called LUVOIR-A. I know things are in development and it's probably not going to launch the way it was initially planned now, but this is basically, as you can see, it kind of just looks like an improved version of JWST. And so for this purpose, it's just going to be able to do a better job of doing transmission spectroscopy. And so this is really going to get us into the sensitivity where we can hopefully start to detect some biosignatures and technosignatures in exoplanet atmospheres. So that's something to look forward to in the next few decades. Now, the fourth category I want to talk about for our search for technosignatures is waste heat and megastructures. So the idea here is basically looking for large structures that block some of their star's light. So kind of one envisioning of this is what you may have heard of as a Dyson sphere, especially maybe in science fiction like Star Trek. So the idea of this would be that as societies grow and their technology grows, the need for energy is just going to continue to rise. And if you're in a solar system, by far the largest source of energy in that system is going to be your star at the center. So the idea here is basically just to set up one gigantic, or maybe a series of like smaller but still very large solar panels to gather energy from a star and put it to some technological use. We use our relatively small solar panels here on Earth, but it's something that someone can build up to if they're looking for larger amounts of energy. So this was another idea proposed in the early days of SETI by Freeman Dyson, to look for stars that look kind of weird because some of their optical starlight is being collected, put towards some technological use, and then re-emitted as lower energy infrared light. And there's this other kind of related idea that we can maybe more generically just refer to as megastructures, which is the idea of large pieces of technology, but not like a solid sphere, because a solid sphere is not really mechanically realistic to produce. But there could be things more like these individual, like smaller solar panels in orbit around a star. And so as these structures orbit a star, if we are viewing the star just from our angle, we're going to see those things periodically passing in front of the star and see really strange patterns in the star's brightness over time. So there are a couple of different projects that are looking for these sorts of things right now. One of them that I want to highlight is called Project Hephaestus. So what they are working on is setting upper limits on the prevalence of partial Dyson spheres in the Milky Way. So this concept of upper limits is something that the SETI community has really started to embrace recently, in that we haven't had any definitive SETI detections yet. But that doesn't teach us nothing about the universe. It can teach us that certain types of technology can't be more common than some value that we can measure. So what they're doing is looking at a bunch of stars, searching for infrared excesses, indicative of this sort of megastructure technology, using optical and infrared telescopes. And what they've determined so far is that fewer than 0.002% of the stars near the sun are consistent with having an infrared excess. So no more than this number of stars look like they could be hosting Dyson spheres. And I want to be very clear that that does not mean that this percentage of stars do host Dyson spheres. It means that this percentage of stars appears to have an infrared excess. The confusion here is that there are other natural factors that can cause stars to have an infrared excess. So especially things like young stars that are still kind of forming might be surrounded by a lot of dust. And this can make them appear different than normal stars do. So what this project is currently doing is now they're following up all of those stars that appear to have infrared excesses. And they're expecting that it's probably going to be dust in most cases, but they need to take a closer look to figure that out for sure and decide whether it's natural causes or whether it could be technology. So that work is still in progress. And then the other megastructure project I want to talk about is going on at the SETI Institute right now. So this is more looking for orbiting megastructures. So what they do is look at stars and how their brightness changes over time. And they're looking for any sorts of weird, strong dips and patterns in light curves. They're just looking for anything that looks really weird in a star's brightness over time. So, and they have found some weird stuff. So you may have heard of a few years ago, this was very big in the media, Tabby star or Boyajian star. This was a star that was observed with the Kepler Space Telescope that ended up having some really strange dips in its light curve. And some people in the media got very excited and said it was megastructures and we definitely found aliens. And it was a little overhyped and not great for the SETI community. But further study has been able to determine actually that there are signatures of natural objects like dust in these transit signals. And so there's no reason to think it's a technological origin. They're pretty sure it's like broken up comets or something like that. I know people are still working on this to figure out exactly what those natural causes are. But this light curve in particular is pretty well determined to be due to natural causes right now. But we're constantly studying stars and we're tracking their light over time. So this project is ongoing as we get more and more data there to see if we can find any more weird stuff. Then after that, follow it up to try to figure out whether it's natural or not. So the fifth category of SETI searches that I want to talk about is called solar system SETI. So this is searching for probes that were sent to our solar system. This was an idea that was proposed in the early days of SETI in the 1960s by Ron Bracewell, who kind of as an alternative to things like radio and laser signals said, why not just send a physical object to communicate? And so I've shown a couple examples here. We have sent some probes out into space. They are traveling slow compared to the speed of light, and they have not reached other star systems yet. But as an example, we've sent out the Voyager probe, and this has on it the Voyager Golden Record. So in the very unlikely scenario, this probe makes it somewhere that there is life in the vastness of space, they're gonna see some information about us. So I will admit that I personally was not initially very sold on the idea of solar system SETI. When I first heard about it, I was like, why would anyone send a probe here? That seems like a lot of work if you can send like a radio signal instead. But this past summer, I was at a conference where Joe Lazio posed the question to us, what is the first thing humans are going to do if we detect a biosignature or a technosignature on an exoplanet? People are going to immediately want to send a probe to take a closer look. So I would say this is not something we're currently doing, but I don't think it's totally in the realm of science fiction. This is something that people are going to be trying to do within the next couple of decades. And the last category is what people call generalized SETI. So this is kind of a really vague idea, but basically the idea is that we don't know what's out there. We have no idea what other life in the universe might be like. So let's just look for anything we find that is weird. So there's not really any specific methods really for me to highlight in this process as like ways to approach this problem, but it's kind of something anyone doing any type of astronomy can do, in that if you find something in your observations that doesn't make any sense, take a closer look and figure out whether it's something natural or whether it might be technology related. So now that I've kind of gone over the main methods, I would like to do our next poll. I want to know if you think we're going to succeed and how.
Very interesting so far, really, Macy. I had no idea there's so many different directions here, so it's really fascinating. So we'll see what the viewers say to this question. So we'll just give them a few more seconds. Okay, here we go. What do you think?
All right, it looks like my favorite answer won.
Yes.
But I have
Mhm.
no real reason to believe that. It's just a personal thought. So the idea they will come to us. This is certainly a popular one. Some people think that they already have come to us. The consensus among astronomers is that we don't have solid evidence of that. But that doesn't mean it can't happen. It certainly requires a lot of energy to build a spaceship and go all the way to another star system. But there's no reason to rule it out. Someone might want to do that. So for intentional messages like radio and laser, again, that's something we as humans don't do. But I don't think it's safe to assume that all other life would be like us. We shouldn't assume that because we don't send out a ton of intentional messages that nobody else would want to, right? So I still think it's really interesting to look for, even though kind of my favorite answer is the next one about unintentional signals. I think I just like this answer because we produce a lot of unintentional signals of technology. We're not trying to communicate, but there are still ways to find us. And it looks like you all agree with me that that's potentially the most interesting one. And then some of you think we won't. And you know, that's very possible. I'm going to talk a little bit for my last part about how we just don't know. So I want to talk a bit about Frank Drake and the Drake equation. Frank Drake was the person who performed the first SETI study, a Project Ozma, and he was one of the main founding people in the field. Frank passed away earlier this year, so we have all been thinking about him a lot in the field. And I want to talk about kind of one of his maybe most recognizable contributions. So this is the Drake equation. This isn't necessarily something he came up with as an equation you want to calculate a definitive answer to, but just kind of as a way to think about all of the factors that go into the search for life in the universe. So in the Drake equation, the kind of n number that you're trying to calculate represents the number of technologically communicative civilizations in the Milky Way galaxy. So the first factor that goes into our equation is the rate of formation of stars in the galaxy. So this is actually a number that astronomers have had some idea of for a long time. It's something like 1 per year. And in the 1960s, when this was first being discussed, this was a number that astronomers knew pretty well. But the next factor here is the fraction of stars that host planetary systems. Now, in the 1960s, we had not detected any exoplanets yet. That didn't happen until the 90s. So at the time, kind of everything from this factor on was based on what we know about Earth. But and the sun and the solar system. But now today, with all of our exoplanet discoveries, astronomers are pretty well determined now that almost every star hosts a planetary system. So this factor in our equation is going to be something like 1. Now, the next factor in the equation is NE, the number of planets per solar system with an environment suitable for life. You might also think about this as like the number of habitable zone planets in a star system, where the habitable zone is something we usually define as a planet that exists at the right temperature where it could hold liquid water, where it's not so cold that it all freezes or so hot that it all evaporates. Because for all types of life that we know and can imagine, water is necessary. Now, it's possible that there are other types of life out there that don't need water, but it's not something that we can imagine or see. So it's something we should be on the lookout for, but is not kind of one of our main assumptions. So the next factor in our equation is the fraction of suitable planets on which life actually appears. And because we haven't found life on any other planets, we have no idea what this number is. We just know that it happened here on Earth. So this factor is for any type of life, including just kind of the first types of life here we had on Earth, like bacteria and things like that. The next factor in our equation is the fraction of life-bearing planets on which intelligent life emerges. So how many of those planets that develop life develop intelligent life? Well, this factor is really complicated because, as I kind of mentioned earlier, defining intelligence is a really difficult thing to do. But on the other side of that, we also still have no numbers because we haven't detected any other life in the universe. So it's a factor that, for multiple reasons, we have a really hard time imagining what it could be. Our next factor is the fraction of civilizations which have this intelligent life already that end up developing detectable technology. And again, we are our only data point here. We ended up doing this, but we don't know if all types of life will. And then our last factor here is the length of time that such civilizations will release these detectable signals into space. And this is a factor that we don't even have our own data point on. We don't know how long we're going to last. So kind of the conclusion here to the Drake equation is that how common life is in the universe is a really, really complicated question. And we are not going to know the answer until we've searched more and we've either found life or we've been able to place really strong upper limits on it. And so you can kind of think about the Drake equation even in the opposite direction, in that performing SETI and getting some idea of what N is from our observations is going to help us learn a bit more about the other factors in this equation. So I want to kind of end with just some kind of philosophy of SETI ideas, and with this quote here that Frank Drake said, actually in the paper where he first described the Drake equation. What he said was, our experience with Project Ozma showed that the constant acquisition of nothing but negative results can be discouraging. A scientist must have some flow of positive results or his interest flags. Thus, any project aimed at the detection of intelligent extraterrestrial life should simultaneously conduct more conventional research. Perhaps time should be divided about equally between conventional research and the intelligent signal search. From our experience, this is the arrangement most likely to produce the quickest success. So this is a sentiment that a lot of us SETI researchers hold. For most of us, SETI is not the only thing that we do. Because, you know, it is discouraging if you do a bunch of SETI searches and you don't find anything. But we still think it's worthwhile, but we often try to do other things at the same time. And when we're taking, you know, various observations of the universe, there is a lot more that you can do with that, even if you don't find extraterrestrial technology. So this idea is something that Freeman Dyson, another founder of the SETI field, called the first law of SETI. The way that he phrased it was that every search for alien civilizations should be planned to give interesting results, even when no aliens are discovered. And I wanted to kind of close with kind of a more modern version of this that one of my colleagues said this past summer at a conference that I really liked. Matthias Suazo, who's involved in the Project Hephaestus, said, I hope to find a Dyson sphere, but if I don't, I hope to find an M dwarf with a debris disk. So I think that's, you know, an important sentiment here in SETI, that even if we're not finding extraterrestrial technology, we're learning something interesting. We're putting limits on how common that technology is. And we're also going to just find some natural astrophysical objects that are interesting. So I kind of want to end on an optimistic note. We are still searching and we still have a lot of hope. But even if we don't find anything, I think we're still doing interesting science.